Hello, welcome to Supercomputer Nepal channel. This is the 8th video that I will be uploading as a tutorial, and this time I am covering Autodock using GPU. So this is the website. I will put the link on the description below. So in this case, to download this package, you can go to the releases here. There are 8 releases so far, and the latest one is December 18th 2021. So this is 1.5.3. You can basically copy this link and download on your machine. Let me copy the link and I'll go to the terminal here. So wget, I will use wget for this and paste the link. So it's being downloaded right now. So finished, download is finished. Now let me extract this. So tar is the command, and minus zxvf is the option, and the actual name that we will be extracting. Okay. So it's done, extraction. Let's see. So we will be seeing now the folder Autodock GPU and the version number 1.5.3. okay. Let's go inside the folder. There you will see some folders and files, and obviously some logo as well right here. The most important thing is you need to have a working CUDA compiler and CUDA library for this. Okay. So first of all, I will show you a quick brief here. Let's check the make file first. What kind of things we need to do? It is written there, and we will modify we will plan accordingly. First of all, the main important thing is you have to define, in order to these two paths you have to give. Okay, so I can give this path as a simply by exporting. Okay, those two are the paths you can export. One is include path of the CUDA compiler, another is the library path in the CUDA. Okay, so let's export the include path first. In particularly my system, where it is I already know. So now type the command export and paste that actual thing, that the GPU include directory, and I know where it is in my system, and you can change this line according to your requirement. Okay, so in this case usr local CUDA and include. Yeah, this is the CUDA include path, and similarly the lib path also. Let me copy this and you can export as such. Very similarly, let's paste that library path is equal to, all will be same except include, you will be writing lib64. Okay, so that's it. And in order to check whether your CUDA compiler works, you can type the command which nvcc. If it gives the link, then you are good to go. Okay, but in my particular case it is from HPC SDK, but it is in other case also. In the actual compiler here from CUDA also you can get, since your version is same, so you should be fine. Okay, either way you can work. Now the next part is on the readme file. The next step is on the readme file. Yes, here, and it is highly recommended to read this file, so that you will be, or you can check this on the browser also, that GitHub page. It doesn't need to be right here, but you can check on there. So this command, this is the command. Let me copy this, okay, right here. But next I will be typing this. Now paste it. Sorry, I think it didn't copy it properly. Let me do again. Sorry, looks like I failed to copy it. Okay, now I hope it might have been copied. Yes, so on the device it is suggested that you type GPU or CUDA, GPU, and in this case you can type power of 2, and recommended are according to your hardware capability, and I am fine with 128. Okay, so that's it. So you can type 64 also. Let's see what will happen. Yeah, looks like there is no error, and we have to check the bin folder if there is some binary file related to Autodock is created. Yes, I can see that file has been created. This is the executable file that we require to the Autodock using GPU. It is much faster than the CPU type of docking, and to showcase the docking speed, I am actually doing flexible docking, which is even involving much time consuming and highly costly calculation. So let's find the path and export this path so that our system will know where the binary is located. So again you can do export, export, export path is equal to, and inside the bracket, that double quotation, paste that path and colon $path and give this thing. So it could be different in your machine because your username might be different, and you might have downloaded this Autodock GPU in different location. Okay, so path could be different than what you have seen here. Now I will go back to the data further down. So I am typically done now. So next part is I will show you how it works and how to launch the program. And I have already a data ready to dock, GPU dock folder, and this, all these examples what I will do here is available in my GitHub page as well, so you can check that later on. I will also show you the data. So this is the target folder of the 6Lu71 protein, and L1 PDBQT is a prototype ligand that I am going to dock on this protein, and affinity.sh is a script to dock single ligand to this protein, and there is another file loopdock.sh. This is particularly for multiple ligands to dock on the same protein and check which one is the best binding, gives the lowest binding affinity, because the binding energy is in negative sign, so I am saying lowest. That is the reason. Okay, and affinity.dat is a file that contains the ligand name, corresponding binding affinity, and the particular pose of that binding. Okay, so we will see that file later. Now let me show you this very file affinity.dat, how I am calling and doing these things. Sorry, affinity.sh file. This is a bash script, simple, to dock a single ligand to a target. Okay, so this is the bash invocation here, and dock the ligand. Actual command to dock this is already in a path. This is the actual executable that will do the docking, and -ff file is after that. We have to call the FLD of the receptor inside that target folder, and -l file is the ligand, which is right here, l1.pdbqt, and this is prepared as a flexible docking. So I have here FlexRes option and the flexible residue also here. Okay, in this pdbqt, and I am checking for 100 different poses. So run is equal to 100, and this is the force field, and this is the output name. Okay, roughly. And next part of the script is extract the minimum binding affinity from the DLG file, and this is just a grep command and some octal, etc. And I will show you this RMSD table. Basically what I am doing here is I am searching RMSD text pattern in this DLG file, and I am printing the last line of that 9 line after this. First, this is a source pattern, and I am writing 9 lines below this source pattern and taking the last line and the 4th column. That is my binding affinity. Okay, and next search is the pose number, which is the 3rd column of the same thing. Okay, and finally I am casting the output on the screen by echo command like this. So let me run this. Let us run and see the result before I talk too much here. Okay, so what you have to do is, this is already made executable. The file can be run directly. So I made the terminal font size little smaller so that we can see all the outputs in one shot. So it's running now. I have Quadro RTX 6000 GPU. So that's it. So this is the typical output on the screen of this run, and it tells us about timing and how the run has been conducted with different columns, generation, evaluations, etc. And the final answer is right here. That means the lowest binding affinity is 6.83 at the 73 number pose. Okay, so this is how we will dock a single ligand on this protein, but generally this is what we do not do in practice. what we do in practice is we collect so many legends. Although I have a legend folder right here, only 5 legends are here, but you can collect as many as you can. Okay, this is the higher the number, better the docking process overall. Okay, so as an pedagogical approach, I have collected only 5, but the thing is you can do as many as. And next time I will be not running this, because this is script for only one legend, but I need as a loop. Since I have many legends, I have to conduct this calculation in a loop. So I have written another script, loop.doc.sh. Let us see how it is. Okay, some parts are very similar to the affinity.sh and some are slightly different. The main difference is the loop and how that loop has been written. Okay, so let me show you. This is again a bash script, by the way, and here is a info about this file, and you can also see this video later on the YouTube channel Supercomputer Nepal. And I am deleting all these files before I run anything. So, and I am creating 2 folders, DLG and XML, to keep the files related to DLG and XML outputs to corresponding folders. And what I am doing here is going inside the legend folder and reading all those PDBQT files as an array, and the overall array name is my league. Okay, and I am coming out of the folder. So array has been created, and next part is the actual docking part. And let me show you how it is here with a little bit bigger font. And now, since I have an array of the file name, and I will pass each file name, each league in my league. My league is an array, but each league is an individual legend. Okay, this is the for loop in bash script, and do is the actual instruction, and this is just for our own convenience, that which legend is running to see on the screen. And actual docking is performed here in this line. Autodock GPU 128 WI is the actual command that we just get after compilation of the source code. And -f file, this line is typically same, except the legends are in a variable. Okay, here, so legends are written in variable. This variable is defined here. So this is the individual legend name out of the array from the legend folder. Okay, so and others are pretty much similar. Extraction of energy from the DLG file, and instead of writing in a terminal, I am writing in a file called affinity.dat file. Okay, and after the run is all complete with the done command here, and I will be pushing DLG file in the DLG folders and all the XML files in the XML folders. So this is how we can do this script, and let's see our result. One quick run, because we don't have much legend, just 5 legends are there, so we can do this live like this. Okay, let me slightly decrease the font, by the way. And now I am running the command. By hitting enter, it will begin running. The 5 calculations will be around. Now the first legend is going on, and this is done. Second is working. Okay, second completed. Now the third is going on. So this way it will cover all the 5 legends, but it is up to you how much legend you have in the folder. And by this particular example, the legends name are also in the array, but it doesn't matter whether they are, it could be differently. Okay, you can just grab the legend on pdbqt name and it will read and makes an array. So I finished 5 dockings here, and the main important is I have all the records in a affinity file. vim, let me check affinity.dat file. Okay, so as I told previously, the first column is the legend name and second column is the binding affinity, and in this particular example legend 3 is the lowest one for the 42 pose number. Okay, this is how it will, and you can later on sort this by like a LibreOffice or Excel program. You can shuffle this in a descending ascending order, but that is what I am not doing today. So typically this is how we do the thing. And one more example I would tell you but will not show you is that the same thing can be done in a supercomputing environment by submitting job. In that particular case, what you will do is you will slightly modify this file with a slalom header. Okay. You will be putting slalom header on the top of this file, and it can be submitted according to the supercomputer, specific to the supercomputer, or PBS also, not only slalom but PBS queuing system also can be done. I will keep that file in my GitHub page, although right now it is not quite made, but in a couple of days I will modify that, possibly tomorrow or the day after tomorrow. And here is the GitHub page. This is my GitHub page. You might have already familiar who are watching this channel. So let's see on the repository, or not quite needed, it is bookmarked here, GPU doc folder. Okay, and in a previous video I was discussing about Quantum Espresso benchmark also, including the compilation with CUDA and OpenMPI. So these results are also here, but let us see the GPU doc folder today. On this folder, typically all the instructions that I have covered before has been written down here on the readme file, and those scripts are here. One is affinity.sh, which is the first script that will be for the single legend, and energy and pose are displayed on the screen. Okay, and the second part is loop.dock.sh. It will for the automatic docking of thousands of or millions of legends, as much as you can collect. Okay, so it does in a loop without any human intervention, and finally you can get the energy, legend and the pose on that file, and you can do further steps of your molecular docking and to check the druggability screening process. And one only missing right here in the at the time of making this video is a slalom script to submit a job in typical supercomputing environment that you can get in few days, possibly in a day or two. Please stay tuned, and obviously if you feel that it is useful to you, this kind of, please encourage my effort by subscribing this Supercomputing Nepal channel, and obviously you can follow this GitHub page as well, so that every day or every week I can make some useful content, and it will be useful for all the high performance computing community, molecular docking, density functional calculations, and many more. And obviously thank you very much, and have a nice day or good evening. Thanks.